So good morning, everyone. We will actually continue. Remember what we were doing in our last class, just a quick recall. And then we will actually continue with the, the utility functions, but we will be done with them today. And so remember what we did is actually in our last class, so we spent a lot of time in, understanding those special utility functions. You're going to see that not only we're going to use them in consumer theory, we're actually going to use them in producer theory as well. So you're going to see, so it's very important. So most of the concepts that we're going to see today and most of the concepts that we actually see in consumer theory, you're going to see that they would be very much related, very similar to the concepts, and sometimes exactly the same, to the concepts that we're going to see in producer theory, okay? So that's why we spend a little bit more time on consumer theory and understanding, these special cases of utility functions and such. And so that you'll see that it will be very useful for producer theory as well. Okay, so the concepts will be very similar. There, we're going to have, instead of indifference curves, we're going to have what we will call isoquants, right? So, and it will be, a curve, like the indifference curve, but this time it's going to show you the bundles of capital and labor, which produces the same amount of output, okay? But don't worry about it, we'll see it later. But the concepts will be very similar. So remember what we learned. We learned about like 3 special cases, but we also said towards the end of the class that actually there is this functional form which kind of like these three perfect substitutes, right? Perfect complements and Cobb-Douglas were actually special cases of this function, okay? And this was basically, remember, so we called it the CES utility function, right? So the CES utility function, CES, so we'll come to this. So this part means constant elasticity of substitution. So there is actually, so we will come to this, what it means, constant elasticity of substitution. But it was, remember, a utility function of like a form, with a form like this, right? Rho plus beta y to the power rho, 1 over rho. So where rho is less than or equal to 1, we said that A is greater than 0, alpha is greater than 0, beta is greater than 0. And we put along the way, we actually, to derive the forms that we considered, we actually put even a bit more restrictions, okay? So this is going to be, and then remember what did we say? So we said that when rho goes to 1, where these things, remember this rho was governing the degree of substitutability, though it's not exactly the elasticity of substitution. So this governs the degree of substitutability. And what was this? Do you remember? So when rho goes to 1, we said these are perfect substitutes, right? So just put 1, so this was the easy case, right? And then you actually get a utility function like this. So let's say A is equal to 1 here. Okay, so this was basically, it was a case where we would have the perfect substitutes, right? So we learned about perfect substitutes, right? And then we actually, we proved all these cases. So, and this is actually, right, so we said that when this goes to minus infinity, this was saying that, the substitutability is very low, right? It's very bad. So what did we call this case? They are perfect complements, right? So we actually called it minimum alpha x, beta y, right? And this is also corresponding to some restrictions. So we put alpha equals to A equals to alpha here, but remember a utility function, you can always get a positive monotone transformation, meaning that you can always put a constant in front of the utility function, right? A positive constant. So basically, so this was the case for perfect complement, and then we said rho goes to, and this was the hardest case, and that was, you guys were going to do that, right, as a sort of homework. So basically, so this was equal to, as a bonus sort of homework, right? So this was equal to what? We learned Cobb-Douglas, right? So it was basically x to the power alpha, y to the power beta. And again, here we had some restrictions, and those were a equals to 1, alpha plus beta equals to 1. But remember, as we said, that we can always take this positive monotone transformation of the utility function, right? But if you want to get this specific form, that's how we did it, right? Now, so these were the case, and you'll see that from now on, we will be dealing with these functional forms, okay? So, but what does this constant elasticity of substitution mean, okay? So what does this guy mean? So apparently, this rho was good. It was telling us something about, you know, the substitutability between these goods, but actually, so this is, it was telling us something, but it's not exactly the elasticity of substitution, okay? So what is the elasticity of substitution? Now, it's actually defined as, so let's write this because it's the definition, okay? So elasticity of substitution is actually this. So usually we denote it by sigma, okay? And it's defined d ln y over x divided by d ln mRs. So basically, it's the percentage change in the ratio of the goods divided by the percentage change, okay, in their respective marginal rate of substitutions. So basically, we know a little bit more. We can actually write this d ln y over x, and then d ln, what is marginal rate of substitution, right? This is what we saw in our previous class. So we figured out that marginal rate of substitution was equal to what? Ux over uy, right? So the ratio of the partial derivatives, right? So basically, so d ln u of x, u of y, okay? So you can actually, so it's the ratio of the marginal utilities, right? So if you want, you can actually write it like this. Marginal utility of x divided by marginal utility of y, okay? So what does this mean? So remember, in this functional form, it says that this is constant, right? So for instance, it's equal to 5 or it's equal to 2, whatever, okay? So constant elasticity of substitution, what does that mean? If you want to change, it means that, you know, like this is just equal to, as I said, a number. If you change the good mix, right? So if you change the ratio of the goods, obviously the marginal rate of substitution will change, right? So let's try to understand. So this is y, x. So suppose I have an indifference curve like this, right? Marginal rate of substitution. Remember, it was defined along an indifference curve, right? So we were keeping utility level the same. So this is actually, so here it says that if you change the goods mix, sort of, suppose you have a y over x ratio here, okay? Suppose you change your good mix, okay? So basically, suppose you come here, and it's actually, so you see that y here, it's like y, x, and let's put this y star, x star, okay? So you see that when you change the good mix, obviously your marginal rate of substitutions will change as well, right? So it says that the percentage change in this good mix divided by this percentage change in the marginal utilities, right? In the ratio of marginal utilities, sort of, I mean in percentage change in marginal rate of substitution, is always one number, okay? And which means that it doesn't matter, right? It doesn't matter that you have a lot of y. You know, if you change the good mix, so you see, if you look at this case, or if you have a case like this, for instance, if you change the good mix here and here, okay? So you change y over x ratio, right? The ratio of the goods, and they will correspond to new marginal rate of substitutions. But apparently, the percentage change in the good mix and the percentage change divided by, like the percentage change in marginal rate of substitution would still be the same number, okay? So it says that it doesn't matter whether you are here, you move from here to here, or you move from here to here, right? The percentage change, it will generate in the marginal rate of substitutions is just a single number, okay? So don't worry about this, but this is what elasticity of substitution means, okay? Now, so in here, according to this definition, what is elasticity of substitution? So, we have our old stuff here. So let's actually write this. So let's actually write this down. So in order to figure out marginal rate, elasticity of substitution, apparently you need to figure out marginal rate of substitution, okay? So let's first try to see the marginal rate of substitution. What is MRS for this guy? So remember, how were we computing that? MRS was, right? So you were you said that, oh, hocam, it's the slope of the indifference curve, absolute value of the slope of the indifference curve, or the easy way to compute it was, right? So the ratio of the marginal utilities, right? Or the partial derivatives, bless you. So this is u of x, u of y, right? But here, do you want to take the derivative of that function, or we can be smart? Right, so let's do what? So let's define a u tilde, right? So what should I do if it's sort of exponential? I take ln's, right? So this is going to be, bless you. So this is, right? So let's actually take, ln, let's not take derivative as we said, right? So it's going to be basically 1 over rho, right? Ln alpha x to the power rho plus beta y to the power rho, right? So you can actually get rid of, this is actually another transformation, you get rid of a's as well, or if you want, you can just keep it, okay? But basically, so this is the case, so let's take this transformation, and then basically we can actually take this guy's derivative, right? So this is okay, u tilde of x, u tilde of y, okay? So basically, if you do this, if I take, like the derivative of these guys with respect to x, what is this? 1 over rho, right? And then I take the derivative of this ln, so 1 over this guy, alpha x to the power rho, beta y to the power rho, right? Times, and then I have to take the derivative with respect to x of, inside. What is it? Alpha times rho times x to the power rho minus 1, right? And this is going to be very similar. So 1 over alpha x rho beta y rho, okay? And then this is beta rho y to the power rho minus 1, right? So you see that these guys cancel out, and then we're left with alpha over beta. Rho's cancel out too. X divided by y rho minus 1. Remember, rho was less than 1, so if you want, you can write it like this. Alpha over beta, y over x, 1 minus rho, okay? Apparently, this is the marginal rate of substitution. So what can actually I say? So do you think this CES utility function is, do you think this is quasi-concave? Remember, it is leading to convex indifference curves, right? Either its utility function is quasi-concave or the indifference curves were convex, right? So how are we checking it? What should we look at? We should check whether MRS is diminishing or not, right? So do you think CS function is quasi-concave? So if you look at here, so remember how are we doing the analysis? We said that when x increases, so you see that this guy will increase. Y, what was happening to y? Y was decreasing, and this guy is positive, right? So what's happening? MRS is decreasing, right? So we can actually say that CES utility function is quasi-concave. What does that mean? It means that, does this mean Cobb-Douglas is quasi-concave? Right? Those were special cases. Does this mean actually that perfect complements is quasi-concave? Yes, right? So it means that all of these guys are just special cases. They're all, quasi-concave. They will all lead to convex indifference curves. Why didn't I say strictly? Which one do you think messes up? Or which ones? Right? So perfect substitutes, for instance, you know that, hocam, it has, right, it's like this. Indifference curves are like this, so it has flat portions, right? For strict, we want these, like Cobb-Douglas style indifference curves. We didn't want flat portions, right? So just keep this CS utility function is quasi-concave. Now, okay, so kind of a, like a bonus quiz or homework. Okay, so now I computed the marginal rate of substitution for you. So just show that. Please show that, of course. Please show that, okay? So the elasticity of substitution for the CES case is actually this. Basically, you find that elasticity of substitution for the CES function is actually this constant number, okay? So for CES utility, what will you do? You know MRS, you're going to take ln, and then you're going to take derivative, right? And then you're going to you'll apply this formula, okay? So that show that we have this, okay? So just keep this in your mind, okay? So that's why it's actually considered as constant, okay? Now, okay, so let's keep this. So now remember, we said that our utility function, we know that it was representing our preferences, right? What lies behind everything was basically, our preference relation. But then we said that our life would be much easier in the function world. So we were dealing with functions, right? So that we could deal with numbers and such. So basically, and then we said that our utility function might have some properties, right? You don't have to have them. You don't have to have convex, right, indifference curves. Your indifference curves could be different, okay? So basically, but it might have some properties. One of them was utility function could be quasi-concave, right? Or we said that utility function could be of this form, right? So it could have a special form. It could be, so we don't know, these are all different types, right? So another property that utility function might have is what we're going to call, it could be homogeneous, okay? Or it could be actually, like we'll see, homothetic, okay? So now let's try to see what, like homogeneity means. And then actually let's see what homotheticity means, okay? So you'll see that these are very important. Again, they will have some sort of a meaning that you can explain to your grandma, okay? So, but you see that some of your friends were asking that these guys, the fact that your preferences can be represented by a utility function, which is quasi-concave, right, strictly quasi-concave, or by a utility function which is of CES form, it has nothing to do with your rationality, okay? So these are just additional properties that your preferences might have, okay? So basically, another property that your utility function might be actually showing is this. So let me write down the definition. And then we'll actually try to understand what it means, okay? So what do we mean by homogeneous function, okay, homogeneity? So this is the definition. So let's write the definition. Right, it's much better to go over the math whenever it's needed, right? Otherwise, we would have covered this in the first 2 weeks, and then probably you would have already forgotten stuff, right? So, but now there is a need, so we'll actually go over the definitions and such. So this is a function, okay? F, let's say x1, x2, xn, is said to be homogeneous, okay, of degree k. So this homogeneity might have some degrees, okay? You'll understand what k is. If, so basically it means this. If I multiply all the arguments, okay, suppose I double all the arguments by a constant t, okay? Then, if this function is homogeneous, you know what happens of degree k? This t pops out and takes the exponent k, okay? And then we write this, okay? So this is, and this should be true for all t greater than 0. So it cannot be only true for, like doubling, when t is equal to 2. But it should be for any t, any constant, any positive constant that you would multiply these arguments with. It pops out, and then if it's homogeneous of degree 5, then it pops out t to the power 5, okay? So basically, it means that, for instance, this will have much more of a meaning when we come to the production theory. But it also has a meaning here as well. For instance, it means this. Suppose utility function is homogeneous of degree, let's say, 1. Right? So let's actually consider the special cases. Suppose, so most of the time you're going to hear homogeneous of degree 1 and homogeneous of degree 0. Okay? So let's see. Homogeneous, and you usually use it homogeneous of degree 1. Okay? So homogeneous of degree 0. So what does this mean, right? If it's homogeneous of degree 1, it means that this is going to be like if I multiply all these arguments by this guy, by this t, then it's going to, this t will pop up, right? T to the power 1, f of x1, x2, xn. Right? So this is basically the case, right? So what does this mean, for instance, in terms of utility? It says that if Harun doubles, for instance, utility function, let's say we have 2 goods. It says that if you double the amount of, chips and, like any drink, Coke, beer, whatever he's having, if you double, what does it mean? So the utility he's going to get from that bundle will double as well, okay? So basically it says that, let's say this is t, so it's t times u of x1, x2, okay? So this is what homogeneity means, okay? So mostly you'll see that in production functions, with production functions, which will be like these utility functions, okay? Or you'll see that, and there you will actually see that this, it means that if I double my capital and my labors, my output will double as well, okay? Or triple, quadruple, whatever, okay? So it is actually, if you have a homogeneous production function, or if you have a homogeneous utility function, it means that. So if you multiply all the arguments by this t, which is a positive constant, it just comes out, it doubles the function's value, sort of, okay? So basically, this is actually it. So, but what about homogeneity of degree 0? Let's do this. It means that if I multiply this function by, again, these arguments by t, this t pops out, and what is the exponent? 0. What does that mean? F of x1, x2, xn. So this is actually, what is this? 1. So what does this mean? So I doubled everything, and the value of the function, it didn't change. So you don't know it right now, but remember, maybe you remember from your introductory econ courses, or maybe you can just figure this out. Suppose in the economy, today I decided to, double all the prices. Or let's think of this, remember they erased the 6 zeros, right? Do you remember? Or you guys are too young? Do you remember? Okay. So it's actually, remember, so they erased 6 zeros. Do you think anything changed about demand for, a cup of tea? Why? When they erase 6 zeros, they erase 6 zeros from prices, but so if they erase 6 zeros from prices, but they left your income with 6 zeros. Would you like that? Yes, right? But unfortunately, what happened? They erased it from the money, right? So it's basically your income also, diminished by, right, 1 million. So did anything change? No, right? So basically, it's actually, so basically, it means that, so you're going to see that demand function, we'll see that demand function, it will be homogeneous of degree 0 in prices and in income, okay? So we'll see, yes?
When I'm going to try to delete the zeros, some economists strictly object.
So it's actually, okay, so here's the issue. I said this, but there is something called, we're going to see, that there could be something called the money illusion. It might have this psychological effect that, things are getting cheaper, okay? So that's why, which is here when we say that demand function is homogeneous of degree 0 in terms of prices and income, we actually think that your grandma, she knows that, when, they erased 6 zeros, they also erased it from her pension, emekli maaşı, and also, right, they erased from all the prices as well. It might be the case that it might have this, sort of effect. People might be under what we call money illusion. They might think that all things are cheaper now, okay? Even though they're not cheaper, they might have this false, impression that things are actually. So you see, these are all sort of ideal cases. The fact that when, when you double all the prices and your income, some people might think that, oh, I'm now richer, right? My income doubles, even though the price of a cup of tea also doubles. I might just think that, I'm richer, right? Because my income has doubled, right? So you had the question, but was it okay? Okay. So basically, so we'll see, okay? We'll see demand function. We haven't seen demand function yet, but these are, you see, very important properties, okay? Now, what we will do is that there is an important sort of note that I would like to make, that, so let's see. Now, if a function is, so let's actually do this, of homogeneous of degree k, we can actually say something about its partial derivatives. What do you think? So if this function f is homogeneous of degree k, its partial derivatives will be homogeneous of degree, guess, k minus 1, k minus 1 actually, okay? So let's show, you'll see that this will be also important. So let's actually show this. So if f, so x1, x2, xn is homogeneous of degree k, okay, then its partial derivatives will be homogeneous of degree k minus 1. Okay, we can actually show this. Okay, it's very, it's easy. But this is important. You'll see that we're going to use them. There's a reason why we consider them right now. Okay, so it's actually, let's write sort of let's sketch the proof. So basically, what does this mean? It means that its partial derivatives, for instance, f1, right? The derivative of this with respect to the first argument, apparently it's homogeneous of degree k minus 1. So if I multiply t, right, all the arguments by t xn, then this is, it says that this t comes out as t to the power k minus 1, f1, x1, x2, xn. Okay, apparently this is the case. Now, how are we going to prove this? Let's use the definition of homogeneity, the original function we know. So we know that function f, but of course for all t greater than 0. So t x1, we know that t x2, t xn is equal to t to the power k, f of x1, x2, xn, okay? Now it says that it's partial derivative, so let's do it for the first one, okay? So you take this guy's derivative with respect to x1, this guy's derivative with respect to x1. So when I take that guy's derivative with respect to x1, this is going to be what? This guy's derivative with respect to the first argument, right? So f1, t x1, t x2, t xn, right? Times, I have to take the derivative of inside as well, right? And times what? T, right? So it's actually, right? So I take the derivative with respect to x1. So I'm trying to reach x1, right? So first I say that, oh, I take the derivative of this guy with respect to the first argument, and then this guy's derivative with respect to x1, right? So this is basically times t, which is equal to, if I take this guy's derivative with respect to x1, what is this? Huh? Yok, this is actually the what it is said here. We're not actually, okay, so the proof starts here. So the proof starts, right? So proof is here. So this is, I wrote whatever this says, right? The partial derivatives are, so if I can get this in my proof, then I'll be done, okay? So I start with this part, because this is what is given to me, right, in the statement. So I'm trying to figure out whether it leads to this guy, okay? So basically, it's so when I take this guy's derivative with respect to x1, so this is just a constant, right? And then, so this is f1, x1, x2, xn, okay? So basically, so you see that tk, so here we're left with t minus 1, t to the power k minus 1, f1, x1, x2, xn, and then f1, tx1, tx2, txn, right? So for all t greater than 0, obviously we have this, right? Okay, so you see that this is basically, we have established the fact. So if a function is homogeneous of degree 1, then its derivatives will be, its partial derivatives will be homogeneous of degree 0, right? So just keep this in your mind. I know that these are, but you'll see where we will use them. And I'll, as I always promise, I'll try to tell you how you can explain these stuff to your grandma, right? Why do we have them in our consumer theory, okay? So basically, so let's actually do this. There is another property which is kind of related to homogeneity, okay? Which is called homotheticity, okay? So these are different stuff. So one is, homogeneity. The other one is homotheticity, okay? But we'll see what it means and the economic interpretation of that as well. And then you'll see that we're going to, so this was the typical example. We're going to link this homotheticity to Rahmi Koç and Akbaba, okay? You know Akbaba, right? So the Behzat Ç. characters. So it's actually, Akbaba or, like Mehmet Amca on the street and, okay, to Rahmi Koç. So you'll see there is a link between homotheticity and you'll see how, okay? So basically, but let me write down, so this is the boring part, but let's do this. Homotheticity, okay, or homothetic functions. So basically, let me write this. A homothetic function okay, is formed by taking a positive monotone transformation of a homogeneous function. Okay? So this is basically, so it's going to be formed by taking a positive monotone transformation of a homogeneous function. So basically, what does this mean? So example, let's say that u xy is homogeneous of degree k. Okay, so let's say, so this is homogeneous of degree k. U tilde xy is when you take a positive monotone transformation of this u guy, okay? So let's say you have this, okay? So basically where h prime, remember when you take the h prime of u is positive, okay? So this is basically what we said. So apparently, if this guy is homogeneous, then this guy is homothetic. Okay, fine. So let me ask you this. Do you think all homogeneous functions are homothetic? All homogeneous functions are homothetic. Think. I have a homogeneous function. I want to write that homogeneous function as a positive monotone transformation of some homogeneous function. What can I pick h? So it's not one, but it's you can, okay, think of this. I pick h this. Do you think it will work? Is this positive monotone transformation? What is h prime? 1. Good. And then I put the homogeneous function in this h. It's going to give me what? Itself. Right? So it's going to give me homogeneous function. So it turns out that all homogeneous functions are homothetic. But the reverse, do you think it's correct? No, the reverse is not correct. Okay? So like all homothetic functions might not be homogeneous. Okay? So the easiest example could be this. I take this h, for instance, h puts u plus 3, a constant. Is this, do you think it's going to work? I take that. Do you think this is homogeneous, this function? remember, it's but maybe this u confuses you. Think of it like this, x plus c. I multiply all the arguments by some constant t. The function should double. You look kind of lost. Okay, so let's do this. So this is, and then we'll give the break, okay? So suppose you have this. I have x1, x2, or I have xy. Okay, it doesn't matter. So suppose I have this, or even let's make it easier. I have this, okay? So now this is basically, let's say that I have the u of x. Now I take this transform, suppose this guy, so suppose I take this transformation. U of x is basically u of x plus some constant c. So suppose this guy is homogeneous, okay, of degree something, meaning that when I multiply it with t, this is t times u of x, right? So do you think it's going to be preserved here? I multiply this guy, so this guy is going to be tx, right? So it would be t times u of x plus c. But what I want, if this is homogeneous of degree something, right? Let's say 1. This is what I write here. I want this, the value of this entire function to double. But this c is going to mess up stuff, right? Because c doesn't double, right? So the function's value, it doesn't double. So this is not equal to t times u of x plus c, right? So you see that that's why homothetic functions, they are not necessarily, all of them, they don't have to be homogeneous, but homogeneous functions, they're necessarily homothetic, okay? So this is basically the case. So let's give a break and then we'll continue, okay?